This Chem Catalyst video is on the solubility product constant, or otherwise called KSP. And since we're going to be talking about solubility, it's important to review a couple rules that we've learned and just the general concept of solubility earlier in the course. You might remember these. These are the solubility guidelines that we've studied, and chemists have studied chemical reactions for a long time now, and they've came up with some patterns in reactivity. And develop some general rules from them, and that is just basically some compounds are soluble, meaning they will dissolve in water, and others are insoluble, meaning they will not dissolve in water, and there are some important exceptions to these rules. The solubility product constant looks at the ratio of products over reactants. And so if we're looking at KSPs for these equations down here, we first of all have to determine if they're soluble or not. Well, sodium nitrate, since according to the first rule, it is nitrates, there's no important exceptions for solubility. This is going to dissociate, and you'll notice that I've done just a forward arrow here into Na plus aqueous plus NO3 minus the nitrate anion aqueous. And so the KSP for this is going to equal just the products over nothing because the reactants are solid, and we never include solids or liquids in KSP equations. So this is going to be the concentration of Na plus times the concentration of NO3 minus. So the KSP for this compound, sodium nitrate, isn't really valuable to us because we assume it to be totally soluble. If we dissolved 1 mole of this, we would predict that we would create 1 mole of Na and 1 mole of nitrate. But substances that are insoluble actually are kind of equilibrium reactions where they only dissociate to a certain extent, right? Magnesium hydroxide is mostly insoluble because it's not one of these exceptions. So it's going to dissolve to produce Mg2 plus 2OH minus, both of which are aqueous. And the KSP for that, the expression would be equal to Mg2 plus times the concentration of OH minus squared. And on a similar note, AgBr is going to dissolve to produce Ag plus Br minus. But keep in mind, these don't dissociate to a great degree because these are insoluble compounds. So I want to show you what that looks like on an actual molecular scale. I guess we can't really look at it, but according to some modeling software, we're going to use a PhET simulation here. But if I take a look at this PhET simulation here where I'm adding table salt, which is very soluble, to water, this is NaCl, you can see here that when it hits the water, the ions break up, and when they break up, they move around in solution. I'm kind of maxing out my computer here, and they're completely dissolved. Okay, so I could keep adding this and it would continue to dissolve. Now, if I look at a slightly soluble salt, though, like silver bromide, which is what we're talking about, I add silver bromide here, and you can see that it dissolves. But if I continue to add a bunch of it, I start to reach saturation. And saturation is when I start to have undissolved ions at the bottom of the beaker here. So keep in mind, this truly is an equilibrium situation. You can see here that I've got ions moving in and out of solution. Right, you can see that down here at the bottom. But then, so some of them are forming a precipitate and some of them are not. Some of them are going from the solid state to the aqueous phase. But the amount stays relatively constant, all right around 45 and 43. So KSP really looks at the product of the soluble ions in a particular solution. And so you can tell that this magnitude of the size of this value tells us a great deal about the extent of the solubility. So just like all chemistry, we're going to want to solve some practice problems dealing with solubility. So let's look at this one. In this case, we're adding solid silver chromate to pure water, And the formula for the silver chromate is Ag2CrO4. Well, since it's a solid, we can write the dissociation equation. It's going to split up to be 2Ag plus, those are aqueous, plus CrO4 minus aqueous. And our KSP here, we don't know what that's equal to, so we're going to have to, we want to calculate that. See, it says, assuming that this is the solution is saturated and there are another important equilibrium volume, Ag and 0 minus, calculate the KSP. So we want to know the KSP. Well, at least we know what we need to solve for. We need to solve for the Ag concentration, and we need to solve for the CrO4 minus concentration. We need to remember that the Ag should be squared because just like our K problems, whenever we have a coefficient, we raise it to that power. So it's going to be an ice chart. But the nice thing is we don't need to even worry about this part. We're only worried about initially what we have here. And it says that there were no other reactions, so that's fine. And our change with this would be plus 2x, this would be plus x. And it says that at equilibrium, we have a silver ion solution of 1.3 times 10 to the negative fourth. Well, now we can figure out what x is, right? X is just going to be equal to 1.3 e, so exponential notation, to the negative fourth divided by 2, which is pretty simple math. And that value is going to be 6.5. X equals 6.5 times 10 to the negative fifth. So that's going to be x. That means this is 0 plus x, so that's just this value here. Right? So now that I have these equilibrium concentrations, the KSP calculation is fairly easy. What I just need to do is plug it in to the KSP equation. So I'm going to get KSP equals the Ag concentration, so that's 1.3 e to the negative fourth squared times the concentration of 6.5 e to the negative fifth. And that's going to give me my KSP value. So I'm going to throw that in the calculator here. So 1.3 e to the negative fourth. I missed that. And I'm going to square that. And then I'm going to multiply that times 6.5 e to the negative fifth. And I get my KSP value of 1.1 times 10 to the negative 12th, I believe is what it is. Yep, 10 to the negative 12th. So that's how I would calculate KSP for a problem like that. Now on the AP, you're likely to see maybe a calculation like this or a couple other variations. So let's look at two other variations. Here we've got calcium fluoride. And we know what the KSP for this is. So I'm going to write that over here. And it's equal to 3.9 e to the negative 11th. And again, it does depend upon temperature. We're not going to factor in the temperature, but usually as temperature increases, the value of KSP will go up. You can think about that in terms of kinetic molecular theory. You've got more molecules in motion, therefore more collisions, and you're going to increase the solubility. Now it says assuming equilibrium is established between solid and dissolved calcium fluoride, and that there are no other important equilibria, calculate the solubility in grams per liter. All right, well, this one's not going to be too bad. We're going to go ahead and write our equation, Ca 2 plus 2F minus. And this is a solid. I need to remember that. I don't want to forget that. These are both aqueous. And then I need to remember just what my KSP expression is. It's always a good idea just to write that so we don't forget that it's Ca 2 plus times the concentration of F minus, and that's squared. Because we never want to forget that. That will totally throw us off. And we're going to do our ice chart here. Do not care at all about the solids, so it's only here. And it says that there's no other important equilibria affecting its solubility. I'll explain what that actually means in the next problem. That just means our initial concentrations are 0. This would go up by x, this would go up by 2x, and again, I'm getting that from the coefficients here, right? That's the coefficient here, coefficient of 1 here. Depends on the stoichiometry. And we get x and 2x for our equilibrium condition. So throwing these back into KSP, KSP equals x times 2x squared, which actually equals x times 4x squared, which equals 4x cubed. So my x value here, which is important because I want to know the solubility in terms of grams per liter. So what I need to figure out is obviously what my x value is. So x is going to be equal to the KSP value divided by 4, and I need the cube root of that. So I'm going to plug that into my calculator over here. So I'm going to get the KSP is 3.9 e to the negative 11th, right? And I want to divide that by 4, right? And then I'm going to raise that to the 1/3 power, and I'm going to end up with 2.1 times 10 to the negative 4th as my x value. 2.1 times 10 to the negative 4th equals x. Now, what does that mean? Well, what that means is that at equilibrium, the concentration of this would be 2.1 times 10 to the minus 4th molar, right? It means that this would be double that because it's 2x, so it would be 4.2 times 10 to the minus 4th molar. So these are the concentrations of the ions. But what's interesting is it says calculate the solubility in grams per liter. So I actually have to work backwards to the salt. Now, since it's a 1-to-1 ratio between calcium and calcium fluoride, I can assume that, based on the KSP, that in 1 liter I would have 2.1 times 10 to the minus 4th moles of CaF2 per 1 liter, right? Because this calcium came from the calcium fluoride. It's a 1-to-1 ratio, so that would be the value. And then I can multiply by the molar mass of calcium fluoride, which is 1 mole, and that'll cancel my moles, right? And the molar mass is 78.1. Again, get that from the periodic table, CaF2. And then that gives me an answer, so I kind of run it out of the room here, of the molar solubility equal to 1.6 times 10 to the negative 2 grams of CaF2 per liter. So sorry that got kind of bunched up down here, but 1.6 times 10 to the negative 2 grams of CaF2 per liter. One more potential application for the AP. And this one involves a common ion. So I did really want to show you this one just so you can practice with it. This one says calculate the molar solubility of calcium fluoride. Now, we have the KSP here. It's 3.9 times 10 to the negative 11th. I'm going to put that up here, equals KSP. And that's kind of sloppy. You can tell that I'm not the best writer on this thing. 10 to the negative 11th equals the KSP. So again, CaF2 is going to be in equilibrium. This is the solid with the calcium ion and 2F minus ions. All right, so I want to know my molar solubility. Okay, so that's moles per liter if we're talking molar solubility. But I'm going to need an ice chart, and these conditions are not going to be 0 because for part A, that's what we're going to do first here, it tells me that I've got 0.010 molar calcium nitrate. Well, this is totally soluble, so this value is 0.010. This value is 0 because I don't have any fluoride in this case. So this is going to go up by x, this is going to go up by 2x, and it has to go up by 2x because the coefficient in it starts at 0. And at equilibrium, I'm going to have 0.010 plus x, and I'm going to have plus 2x here. Now, we've done common ion effect before. It's just like a common ion problem in an acid-base equilibria. I'm going to set this equal to my KSP. My KSP in this case is going to equal this, which is 0.010. I'm going to assume the x is negligible based on the KSP, which is a fair assumption, and I'm going to multiply that times 2x squared. Well, you can see where this is going. Basically, my KSP is going to equal 0.010 times 4x squared, which is really 0.04x squared. And I'm going to solve that. I'm going to take this back over here. I'm going to solve that value for x. So x is going to equal my KSP, which is 3.9 times 10 to the negative 11th divided by 0.04 square rooted. Right? So let's plug that into my equation here. I got 3.9 10 to the negative 11th divided by 0.04. And again, I need the square root of that. Square root, second answer, and I end up with 3.1. Sig figs 3.1. I should have had 2 there. So 3.1 times 10 to the negative 5th. So what does this tell me? Well, that's my x value. Again, going back to the stoichiometry. If you think about it, this really went down by x because the coefficient is 1 here and it's 1 here. So if this went up by x, the value of this, the molar solubility, is just this value right here. I would expect it to be 3.1 times 10 to the negative 5th moles of CaF2 per 1 liter. And you might be saying, what about this? Well, I'm not including this because it's not affecting it. I only wanted to figure out what the x value is. It's negligible with regard to this 0.01, but it does increase because I'm also making the F minus. Now let's look at part B here. I'm going to have to go up here and look at the problem again. Part B tells me that in this case I have 0.010 molar NaF. Okay, so this case the other ion is going to be affecting the equilibria. So let's go back up here just a second so we can compare these two. Right to there. Okay, apparently it wants to go all the way to the top. So if I have CaF2, it's an equilibrium, with Ca2 plus 2F minus, in this case I've got 0.010 molar NaF. So that means that this solution is now 0 0.010 molar, right? So this is 0, this is plus x, this is plus 2x, and this is x, and this is 0.010 plus 2x. And again, I'm going to avoid the 2x here, or assume that it is negligible, and my KSP equals 3.9 times 10 to the negative 11th. That doesn't change because the temperature doesn't change. So we got to go solve for this value. So now I get my KSP equal to x, right, because that's this x, times, let's put x in here for that, times this term, but it's going to be, we're assuming the x is negligible, or the 2x went 0, 1, 0, and this has to be squared. That's my KSP expression. So now my x value equals KSP divided by 0.010 squared, which that's easy enough to figure out. We'll get the calculator out here. We get our KSP, which is, again, I'm taking it up here, 3.9 times 10 to the negative 11th, and we divide that by 0.010, and that's going to be squared, and we end up with 3.9 times 10 to the negative 7th. Right? So the molar solubility in this case is going to be 3.9 times 10 to the negative 7th moles of CaF2 per 1 liter of CaF2, which makes sense. Okay, and why does it make sense? Well, F minus, you had equal concentrations of F minus and Ca2 plus, but in this case, you're actually driving the solubility down a little bit more because there are 2 F minuses for every 1 calcium fluoride.